Here's the hydroboration oxidation of alkyne reaction. So we start with our alkyne, and once again, usually it's a terminal alkyne, right? So here's your hydrogen here, and on the other side of our triple bond, let's say there's some R group attached to this carbon. So to our alkyne, we're going to add, in the first step, borane, BH3, in THF as our solvent, and in the second step, we're going to add hydrogen peroxide and hydroxide anion OH minus, and we're going to get addition of water across our double bond. So it's very similar to the last reaction. The difference here is the regiochemistry, right? This regiochemistry is actually anti-Markovnikov addition. So this is anti-Mark's rule, right? So anti-Markovnikov meaning the OH is going to add to the least substituted carbon, which of course must be the carbon over here on the left. So we end up adding H2O, water, across our triple bond. So now there's a double bond present, and then there's an OH in our molecule. So just like in the last video, we form an enol here, like that. And the enol, of course, is not the most stable form. We're going to get some rearrangement, and we're going to end up with an aldehyde here. So we can see we get an aldehyde functional group from a terminal alkyne undergoing this reaction. Now, sometimes if you use borane in this first step over here, sometimes borane is so reactive that it's actually going to add two molecules across your triple bond, since your triple bond consists of two pi bonds. So sometimes you'll see a different molecule used. Sometimes you'll see a dialkyl borane. So put two alkyl groups. I'll put R2BH. And if you make them really bulky, this steric hindrance prevents the second addition of the borane, because in the mechanism you want only one addition of the borane, and the borane is going to add on to the same carbon that the OH does. So check out the video on hydroboration oxidation of alkenes for much more detail of that first mechanism that we discussed. So the net result of this reaction is to form an aldehyde from your terminal alkyne. So let's look at a reaction here. So let's make our triple bond right here, like that, and we'll make it a terminal alkyne, and we'll make this side a benzene ring. So we'll make a rather large R group here. So let me put in some electrons on my benzene ring. So let's just go like that. All right, so if I react this alkyne, right, with either a dialkyl borane, or I'll just put borane here, and you can use a dialkyl borane if you want to, or whatever your professor wants to use, in THF, and second step, hydrogen peroxide and OH minus, like that. So the first thing you have to think about is, okay, what's going to happen? I'm going to be adding water across my triple bond, and I need to think about what side gets the hydrogen and what side gets the OH. So once again, I have two choices, right? I could add the OH onto the carbon on the right, or I could add the OH to the carbon on the left. And the regiochemistry here is anti-Markovnikov, so I'm going to add that OH to the least substituted carbon, which of course is the carbon on the right side. So I'm going to end up adding the OH to the carbon on the right side. So let's go ahead and draw our double bond in here. First, let's go ahead and draw our benzene ring. So I'll go ahead and make it like this. And that benzene ring is connected to a carbon, right? This carbon right here. There's now a double bond present, like that. And I added the OH to the least substituted carbon. I added the OH to the carbon on the right, like that. And I added a hydrogen to the carbon on the left. So that's adding my H2O across my triple bond. And then there was still a hydrogen on this carbon on the right, like that. So that's my enol intermediate, like that. So let's take a look at what's going to happen to that enol intermediate. It's going to rearrange, and in the last video we saw an acid catalyzed tautomerization. In this video, base is present. Right, so we have our hydroxide anions in solution. So let's go ahead and redraw our enol and show the enol reacting with base. So let's go ahead and draw the enol here again. So I'll draw that enol on the right side. So there's my benzene ring, and I have my double bond in here like that, and I know I have an OH like that, and put in my lone pairs of electrons. And I'm going to react this with hydroxide anions, right? So hydroxide anions are floating around. Hydroxide's negatively charged, so hydroxide will function as a base. Right, so let me get in my lone pairs of electrons here on my oxygen, and going to pick up that proton, right, and kick these electrons off onto this oxygen. So let's go ahead and draw the result of that acid-base reaction, right? So it's an equilibrium. So let me go ahead and draw my equilibrium arrows like that. So what's going to happen? I have my benzene ring still, and I have my double bond, and let's see, now I have my oxygen with 3 lone pairs of electrons around it like that, so negatively charged. So now I can draw a resonance structure for this molecule, right? So let's go ahead and put in our resonance brackets here like that. So what can I do to move that, to spread that formal charge out throughout the molecule? Well, I could take a lone pair of electrons right here, and I could move it into here to form a double bond, and that would give too many bonds to this carbon. So the pi bond in here is going to break, and the 2 electrons here are going to move out onto this carbon like that. So let's go ahead and draw the result of the movement of those electrons. I still have my benzene ring like that, and there's my carbon skeleton here. Now I have a carbon double bonded to an oxygen. There used to be 3 lone pairs of electrons around this top oxygen. 1 moved in to form the double bond, so now there's only 2 lone pairs like that. And the electrons that used to be in this pi bond have moved onto this carbon right here. So this carbon right here is still bonded to another hydrogen, so the 2 electrons moving out onto it are actually going to form a carb anion here. So this is actually a negatively charged carb anion like that. And water is now present, right? OH minus picks up a proton to become H2O, so now water is floating around like that. So now water is actually going to function as an acid. It's going to donate a proton, and this lone pair of electrons are going to take that proton. So they take that proton and kick these electrons in here off onto the oxygen atom like that. This is an acid-base reaction, so this is going to be at equilibrium. We need to go ahead and put in our other resonance bracket like that. So what are we going to get? We still have our benzene ring untouched over here. And let's see, now we have our carbonyl like that, right? And we just added on a proton to this carbon right here like that. So now we are done. And you can see this is an aldehyde, right? I didn't draw on the hydrogen over here, so you can leave that out if you want to. But if you want to draw on your hydrogen, there's a hydrogen there. There's also a hydrogen on this carbon right here. I just didn't draw it in to show some clarity in the mechanism. So the end result is we form we form an aldehyde from a terminal alkyne, and we showed this tautomerization using base. So let me just go ahead and write one more thing here. This is an example of a base catalyzed tautomerization, right, where we go from the enol form, right, to, in this case, an aldehyde as your product, which is more stable because of the carbon-oxygen double bond.